experiment, often we're collecting a large amount of data, measuring things several times, having several groups. We want a large sample size. So we generally have a large quantity of data. And just a list of numbers. Is there no packet? Not going out. Maybe. So rather than just adding a long list of numbers and data, we often will use statistics to help us sort of make sense of our data. Statistics help us understand, they sort of summarize the data that we collected in our experiment. You guys told me that you learned some statistics last year in algebra. That's good. Some of the things we talked about today are going to be familiar to you from that. We kind of different categories of statistics that we sometimes use when we're looking at our data. One broad group of statistics are called descriptive statistics. These are kind of statistics that sort of summarize our data. And within descriptive statistics, there's a few categories. The packet you picked up in the beginning talks about some of these descriptive statistics. These are ones that are mostly familiar to you. Some statistics are used to measure what we're called central tendency, measures of the average. We have a huge number of data points. You might want to know, okay, well, where is sort of the center of that data? So the common statistics that I know you're familiar with, the median, the mean, the mode, those are measures of central tendency. They're measures of the average. If I were to measure the height of everyone in the classroom, I could then find the mean of the height, and that would tell us about where the middle of our height is. I mean, some people are taller, some people are shorter, it's the average. How about median? When would median be a better measurement of central tendency? Yeah, when there's an outlier. If we happen to have a single individual here that was 6'8", that would weight our average and bring it up quite a bit with a small sample like this. Whereas, what is the median exactly?
It's yeah, it's like the middle when you're including
Yeah, if you rank all of your numbers in an increasing ascending order, the middle one is the median. And so having one outlier either above or below the average doesn't change the median very much, just moves it up one notch. Whereas for calculating the average or the mean, that would influence it more. We also use measures of how variable our data is, how spread out. One simple method is looking at the range of data, the difference between the largest and smallest. That tells us sort of how spread out our data is. If we're talking about height, if I found that everyone in this classroom was between 5'6" and 5'8" inches, that's a pretty narrow set of data. Okay? There's not a lot of variation above or below that. Standard deviation is another way we can look at measurements of variability and variance. We also have what we call measures of confidence. So if I wanted to try to understand the height of ninth graders, what would be the very best way for me to do that? Get every ninth grader and measure their height. And I have the whole population. It's very clear. That's sometimes not practical. So if I consider this class a sample of ninth graders, I could measure your height and use that to try to understand the height of ninth graders in general. Now, would it be perfect? No. Would the average height of this class be the same as the height of every ninth grader? No, but might be close. Measures of confidence allow us to sort of understand how confident can I be that the height of this class is similar to the height of all ninth graders in general. We can do some statistics on confidence intervals for the standard error that we could say, okay, I'm 95% sure that the average height of all ninth graders is between this and this. Okay? So we're reasonably confident, 95% confident. So that's another way. Have you guys ever worked with those confidence intervals? Okay. Then we have something else called inferential statistics. These are often used to test a hypothesis. So for example, if I had some plants I was growing, and some I were giving fertilizer, some I was not, collected data on 100 plants over a 2-week period, okay, I would have two sets of data. I would measure the height of those two groups of plants. So let's say one group of plants, the height was 10.8 centimeters after 2 weeks. The second group, that was the group that got fertilized. The group that did not get fertilizer, the control group, was 10.6 centimeters on average. So does giving them fertilizer cause them to grow taller? What do you think? 10.8 versus 10.6? No? Yes, you're kind of unsure. You can't be sure exactly. That's a pretty small difference. So is that difference due to the fertilizer, or is it just random chance that they happen to be different? That are they basically the same average? We have tests that can help us understand that. And one that we're going to be doing today is called the t-test. We would use a t-test in that example that I was just telling you about. We would look at the means of both groups, and the t-test tells us, well, is the mean of my fertilized plants and unfertilized plants actually different? Or are any differences just due to chance? And again, you can set up how confident you want to be. In biology, typically we use 95%. Say, okay, I'm 95% sure the mean height of the fertilized plants is different than the unfertilized plants. Other statistics we can use to test hypotheses are the chi-square test. Helps us to observe, to determine if what we're observing, the frequency of something, matches what we would predict. Sometimes we use that in like genetics research, for example, to see if the results of a cross between two parents matches with what we would expect based on certain genetics. You guys heard of regression? Or correlation. Correlation allows us to understand if two sets of data are correlated, if they sort of move together. One is dependent on the other. I have here three graphs, just of whatever random data. We have an X and a Y axis, we have data points. In this case, do variable X and Y, are they correlated? Is one move when the other does? If you increase X, what happens to Y? It also increases. That's a pretty strong correlation. How about this one? No correlation? Are the higher X values also higher Y values? Yeah, there is some correlation here. Not as strong as this one, more variability in the data, but I would say there's probably still some correlation. And how about this one? no correlation. So we have some statistics we can do that could tell us how closely tied are this x and y variable. Okay? Are they, 90% of the variability in y depends on x, or is it a little bit? The other thing we do related to our data is try to visualize it. Try to make it from a list of numbers into a format we can see. Sometimes visualizing our data in a graph of some sort allows us to sort of understand it better, to see patterns, to see trends. And so we might graph it. Here's a few examples of different types of graphs that you might use this year. Type of graph is this?
Bar graph?
Bar graph. Do you call it anything different? What do you call it in math? Do you call it a bar graph? Or histogram? Okay. If we're looking at frequencies. But yeah, this is a bar graph. Shows us, the rate of salmonella over time. What's this type of graph? Simple line graph. Okay, we show continuous data over, in this case, period of time. See trends and how things move. Love that one. I know you guys learned about this, right? I remember what it's called? Box plot. Yeah. Gives us information about various samples, the maximum, the minimum, quartiles, the mean. You know what this is called? Just data points, Sophia?
Dot plot.
What's that?
I call it dot plot.
Is that what you called it in math? Scatter plot? Yeah, I call it scatter plot. Both? Okay. Where you just are plotting your data points. What do you think this line represents? That's not data.
Line of best fit.
Yeah, line of best, or that tells you how closely correlated they are. You think, are these data closely correlated? Not really. I mean, they're pretty spread out there. But again, then we have these measurements tell us how closely correlated they are. This measurement of R. All right. So we're going to use some of these statistics today. And that's what some of those packets I gave you were for. So we'll look at a couple of those things.